Or even more simply, this lesson teaches RYA coastal skipper and yachtmaster students all they need to know about estimated positions. In millennia before ubiquitous availability of satellite navigation and its land-based forerunners Decca, Loran and radio direction finding, fixing the ship's position out of sight of land was the navigator's most challenging task. Determining latitude was relatively easy, unless the sky was totally overcast, in that it could be found from the altitude of the sun at noon, with the aid of a table giving the sun's declination for the day, or even more simply, in the northern hemisphere, from the altitude of the pole star. However, longitude was an entirely different matter, because it can only be found if you can very accurately measure time. Before the mid-18th century, when German astronomer Tobias Mayer, in collaboration with Swiss mathematician Leonhard Euler, developed a means of doing this by observing the moon's position relative to other heavenly bodies, and very soon thereafter English clockmaker John Harrison perfected the chronometer, ocean navigators had to rely on dead reckoning, based solely on the compass and an estimate of distance run according to their primitive logs. This was potentially highly inaccurate on long voyages out of sight of land, which sometimes ended in tragedy as a result. Even after the chronometer had solved the longitude problem, right up until the age of electronic navigation, calculating an estimated position based on the distance you have sailed from your origin, plus an estimate of the tidal streams or currents you've suffered, was the only means of fixing position, if it were impossible to obtain a sight on some charted or heavenly body. It's tempting to believe that, with the universal availability of satellite navigation systems, working up an estimated position is no longer relevant for the 21st century navigator. However, all electronic devices suffer the possibility of multiple points of failure, and the GPS system in particular has multiple vulnerabilities, which we'll cover later in this course, and cannot be 100% relied upon. And even if GPS does allow us to fix our position with remarkable accuracy, a forward estimated position is an extremely valuable tool for predicting our course over the ground when sailing close hauled. Let's start with a simple estimated position based on a starting fix at 1000 UT at outer end of the transit in and out of Colville, when our log reads 2.5 miles, our best course to windward is 051 degrees magnetic, the tide is setting 116 degrees true, 2.9 knots for the entire hour, and an 1100 log reading of 8.5 miles. (051 degrees magnetic minus 6 degrees of westerly variation gives a true course of 045 degrees, and we plot this away from our 1000 fix, giving the line 1 arrowhead for water track. The distance run on our log from 1000 to 1100 is 6 miles, so we measure this down the water track and strike across to make our dead reckoning position, which is where we might be in the absence of tide. Next, we mark off a vector representing the tide we have suffered over the hour, so 116 degrees true, 2.9 miles, to give our estimated position, which is represented by a triangle. The tidal vector is denoted by 3 arrows. And, of course, we must make a note of the time and log reading alongside the estimated position. There's no reason why you shouldn't plot an estimated position for a period longer than or shorter than an hour. Here we've sailed 8 miles on a spring tide on 240 degrees true, starting 30 minutes after high water Victoria, and, according to tidal diamond A at Springs, we've suffered 1 hour of tide at 170 degrees at 0.5 knots, and the second hour of 111 degrees at 1.6 knots. Geometrically, we get exactly the same end result if we plot two 1-hour estimated positions. Now let's take a look at using a forward estimated position to determine whether we are on a safe course. Imagine that we're under sail, racing, from Colville to Sweetwater, and every second counts. The wind is in the west, and the best course we can make to windward is 222 degrees true at 4 knots. It's neap tides, and at 2300, 1 hour 30 minutes before high water Victoria, we fix our position northeast of Stevens Rock. We are anxious to weather Cape Don and False Cape without tacking. Will we make it? We plot a water track 222 degrees, 4 miles from our fix, and from the end of this a tidal vector 095 degrees, 1.9 miles, to give a predicted 0-100 hours estimated position. If we join our fix to our predicted EP, we can see our predicted ground track, or, as is more often called these days, course over the ground, or simply COG. This tells us that we should weather Cape Don into Jackson Bay, but then it's going to be touch and go whether we can also make it round False Cape. Until now we've ignored leeway, but see here how just 5 degrees of leeway could have a catastrophic effect on your assumption that you should clear Cape Don. Now let's take a look at plotting an estimated position, or EP, from scratch. I suggest that you follow along on RYA Chart 3. Imagine it's the 21st of June. We're bound from Sand Key to Dunbarton in a southwesterly force 5. Before we depart, as part of our passage plan, we carefully examine the tidal atlas so that we know exactly what the tide will be doing each hour of our passage. Here we're particularly focusing on the period 12:30 to 14:30, when we'll be in the middle of the Lawrence Channel. We calculate that between 12:30 and 13:30 the stream will be setting 293 degrees at 3 knots, and between 13:30 and 1400 274 degrees at 2.6 knots. We note the traffic separation scheme and determine to navigate just outside its western end, but in order to cross the very busy shipping lanes as quickly and safely as possible, we aim to steer perpendicular to the lanes. At 12:30 Northern Peninsula Daylight Saving Time, when our log reads 5.6 miles, we fix our position by GPS as 045 degrees 58 minutes north, 006 degrees west, and alter course to 010 degrees. At 12:45 we sail into thick fog, but because we're equipped with both radar and AIS, we continue heading north. Just before 13:15, when we go below to plot a fix, we notice that our batteries are almost flat, and when we tried to start the engine, nothing. Fortunately, we make a note of the log reading, which is 10.1 miles, just before all our electronics fail. Well, as they say, it happens. With lots of shipping about, and knowing that we must be just west of the entrance and exit to the TSS, we decide we have no choice but to maintain our course, keeping a very vigilant watch, and everything crossed. In addition to the sound of numerous ships' whistles, we can hear the lighthouse on Cape Bramshaw somewhere ahead. Just before 1400, we hear waves breaking ahead. What should we do? We urgently need an estimated position. Our compass course since 12:30 has been 010 degrees, and we adjust it for deviation, which, according to our deviation card, is approximately 3 degrees west, and variation 6 degrees west, giving a true course of 001 degrees. However, we need an estimate for leeway, and our experience with this yacht on a beam reach in force 5 tells us we should allow 4 degrees. So we end up with a water track of 005 degrees. Our last log reading before all our instruments went down was 10.1 at 13:15, which tells us that in the 45 minutes 12:30 to 13:15 we covered 4.5 miles on the log, so an average speed of 6 knots. By 1400 we will therefore have sailed 9 miles, so we measure this off on the water track to find our dead reckoning position, from where we plot two tidal vectors, the first for 1230 to 1330, 293 degrees for 3 miles, and the second for 1330 to 1400, 274 degrees for 1.3 miles, to find our estimated position, which tells us we're in a bit of a pickle. What would you do now? You need to act very quickly, but an estimated position is just what it says it is, an estimated position. And in the absence of a fix, you need to take a realistic view of how accurate, or probably inaccurate, it's likely to be. OK, time's running out, but can you rely on your estimated position and turn to starboard to follow along the coastline to Cape Balshaw and Cohen Rock? Imagine that your log were under-reading by 2%, that your helmsman had actually steered 008 degrees, that leeway wasn't 4 degrees but 2 degrees, and that the tidal streams today are 10% stronger than predicted because the wind has been blowing hard from the west for days, setting up a surface current. These really are comparatively small errors, and well within the range of possibility, but boy, do they add up! Now plot an estimated position based on these new numbers, keeping the original estimated position triangle on the chart so you can see how far out you might be. Your new plot should be approximately 1 mile west of your original estimated position. That's approximately 10% of the distance run. So if it's crucial, draw a big circle round your original 1400 estimated position. This is known as a circle of uncertainty. In other words, you could be anywhere in the circle, and then navigate your circle of uncertainty away from danger. Remember, the wind is in the southwest, so you can only sail approximately west or south, then southeast, then roughly northeast, keeping your circle of uncertainty well away from danger. All the time desperately hoping to get a fix on something. If your echo sounder were working, it might give some reassurance, but you lost it, along with all your other 21st century navigation aids. It was in situations like this that navigators of old shed years off their lives. Have a good think about how the situation might have been avoided, and tell me what you think via the Resources tab. Now let's take a further look at future or predicted estimated positions. Again, I suggest that you follow along on your chart 3. Imagine that at high water Victoria, plus 3 hours and 30 minutes, you are at position 46 degrees, 01 minutes north, 006 degrees, 12 minutes west, and, once again, intent on beating round Cape Don and False Cape to Sweetwater. The wind is in the west, as it always is when that's where you want to go, and the best course you can make to windward, allowing for 5 degrees of leeway, is 320 degrees true at 5 knots. It's neaps, and the tide is 290 degrees, 1.5 knots. If you plot an estimated position 1 hour out, AB equals 320 degrees, 5 miles. BC equals 290 degrees, 1.5 miles. You can see that your predicted estimated position, C, places you roughly 2 miles due north of Stevens Rock, and if you were to measure the course and distance from your fix, A, to the estimated position, C, you'd find that your course over the ground, COG, is 313 degrees, true, and your speed over the ground, SOG, is 6.3 knots. These can be verified from your GPS. The question is, when should we tack to efficiently and safely weather Cape Don, whilst at the same time avoiding the worst of Stevens' race by keeping close inshore? Here's where, if you're under sail, you need to know your boat and, specifically, her likely tacking angle in the prevailing conditions. By this we mean if, for example, we were sailing efficiently on port tack and recorded our compass course, by how many degrees would it reduce after we've tacked? The answer will vary boat by boat, according to the conditions and how well she's being sailed. It might range from perhaps 80 degrees for a well-sailed racing yacht to 120 degrees or more for something at the other end of the performance spectrum. In this case, let's imagine that it's 95 degrees, and that we're allowing another 5 degrees for leeway on both tacks. Our tacking angle will be 105 degrees. So, if our water track on port tack is 320 degrees, it will be 320 minus 95 minus 10 equals 215 degrees. Anywhere on your chart, draw a water track DE of 215 degrees, 5 miles, and a tidal vector EF of 290 degrees, 1.5 knots, and join the end of the tidal vector F back to the origin D to find the predicted COG, DF. In this instance, it's 230 degrees. Draw a circle round Cape Don, the diameter dependent on your intended closest point of approach, allowing a safety margin, and plot a line parallel to your predicted COG of 230 degrees at a tangent to this circle, at point G, to extend back to intersect your original COG, AC. You can tack at the point of intersection, H, and if you measure AH, you'll find that it's a distance of 3.15 miles, which at 6.3 knots will take you exactly 30 minutes. Closely related to calculating an estimated position is the transferred position line fix, or, as it's sometimes known, the running fix. It is used when you only have one charted feature available to take a compass bearing from. For example, a distinctive lighthouse on an otherwise featureless coast. The lighthouse on St. Anthony's Head is an excellent example, especially at night and close inshore, when the next light down the coast, Cape Balshore, is obscured. The basic idea is that you take the bearing on the charted feature, and, remembering to allow for magnetic variation, you plot a position line and record the time and log reading. After some while, when the bearing has increased or decreased significantly, you plot a second position line and again record the time and log reading. Then plot an estimated position with its origin based anywhere on the first position line, using the distance run, in this case 2 miles, and an estimate for the tide you will have suffered over the period, which is 15 minutes in this example. Finally, you draw a line parallel to the first position line from the estimated position to intercept the second position line. This gives you a fix. Note that the fix can be drawn as an oval, because whereas we know that at 2015 we were on the position line, our estimated position plot will be subject to the usual errors. If we were using the fix to ensure that we were sailing a safe distance off the shoreline, we would assume that we were at the end of the oval nearest to danger, and navigate accordingly. The correct symbol for a transferred position line is as shown. Note that it doesn't matter where in the original position line you commence your estimated position plot. The transferred position line takes care of this geometrically. OK, let's imagine it's a beautiful March morning, sunny and not a drop of wind. We are motoring on a passage from Victoria, south along the coast on our way to Dunbarton. It's our first time out this year, and we've discovered after we'd departed that the GPS has given up the ghost. We need a fix to make sure that we maintain a course which will keep us clear of the hazards off Cape Woodward, especially since the tides set very strongly at times. At 1100 UT, St. Anthony's Light bears 112 degrees magnetic. Our compass course is 165 degrees, and the log reads 23.5. We enter all this in our log. 20 minutes later, the light bears 038 degrees magnetic. We have kept a compass course of 165 degrees, and the log reads 25.5.
High water Victoria is at 1318 UT, so we need to use the set and drift at high water -2, taking account that today's range is 3.7 metres. Tidal diamond E is close, and from the table at the top of chart 3, we can see that the stream will be setting 1.7 knots on an average neap tide and 3.4 knots on an average spring tide at 124 degrees.
By interpolation, we calculate that the stream will be setting us 2.6 knots at 124 degrees. We need to convert our compass course steered, 165 degrees, by adding 5 degrees of deviation and subtracting 6 degrees of variation, arriving at a true water track of 164 degrees. Our log reading at 11:20 is 25.5 miles, so we subtract 23.5 to get a distance sailed through the water of 2 miles. Remembering to subtract 6 degrees of variation from the bearings we took at 1100 and 1120, we plot 2 position lines away from the lighthouse, the first at 106 degrees, the second at 032 degrees. We should write the time and log readings alongside them. Then we plot a water track of 2 miles at 164 degrees from an arbitrary position somewhere on the 1100 position line, and from the end of that a tidal vector of 0.9 miles at 124 degrees, representing how the tide will set us over the period 1100 to 1120. Finally, we draw a transferred position line parallel to the 1100 position line from the end of the tidal vector to intersect the 1120 position line and mark our fix. If we assume a worst-case scenario that we are at the end of our fix closest to the shore, and then project our water track forward from there, you can see that we should clear well south of Cape Woodward. Well done! You've completed the lesson on estimated positions. Now go on to attempt exercise F.